guys, my name is Craig and welcome to Peri Solutions. In today's video, we're going to talk about solving equations that involve complex numbers. And in this video, we're going to look at polynomial equations with solutions that may be complex numbers. Right? So what we need to know is that if z is equal to x plus iy is a root of a polynomial equation with real coefficients, then its complex conjugate, which is equal to x minus iy, is also a root of a polynomial equation where the complex conjugate, right, z star there is a complex conjugate of z, right? So this is a very important result that we have to know, which we shall apply to these questions. So to start off with number one, we're told that a cubic equation with real coefficients has three roots, right? Two of the roots are 2 and 1 plus root 3i. First question says write down the third root. So applying this, the third root will be the complex conjugate of this complex number, which is 1 minus root 3i. So this is the third root. The second question says, second part says, find the equation which is these three roots. Write it in the form az to the power of 3 plus bz squared plus c plus d is equal to 0. So if we have these three factors, these three roots, we're going to write them in terms of factors, or in other words, we're going to write them as factors. So if z is equal to 2 is a root, then z minus 2 is a factor. And then if z is equal to 1 plus root 3i is a root, then z minus 1 minus root 3i is a factor, right? And as well, we do the same for 1 minus root 3i. So we're saying z minus 2 times z minus 1 minus root 3i, then times z minus 1 plus root 3i, right? So it came out multiplication. We say z minus 2, we leave it like that. Then we start by expanding these two. Z times z, we get a z squared. And then z times minus 1, that's minus z. Z times that, we get plus root 3zi. Then minus 1 times that, we get a minus z. Minus 1 times minus 1, we get a plus 1. Minus 1 times that, we get a plus root 3i. Then root 3i times z, we get minus root 3i times z, we get minus root 3zi. Then minus root 3i times minus 1, we get a plus root 3i. And minus root 3i times root 3i, we get a minus 3i squared, which is just same plus 3. Then we close the bracket like that. So now if we simplify the common factors, if we group the like terms, we see that we've got this, right, plus root 3zi, right, then minus root 3zi. That will go with, this will give us a 0. And then what else do we also have? We also have, this was supposed to go, okay, let's cross check again. So z times, okay, this is correct. For z, this will be correct. Then for minus z, yeah. So for minus 1 times z, that's minus z. And minus 1 times minus 1, that's a plus 1. Minus 1 times root 3i, that will give us a minus root 3i. So minus root 3i, such that this minus root 3i plus root 3i will give us a 0. And then we end up having z minus 2 times z squared minus z, that's minus 2z. And then 1 plus 3, we get a plus 4. So now if we expand, we're saying z times z squared, that's z cubed. Z times minus 2z, that's minus 2z squared. Z times 4, that's plus 4z. Minus 2 times z squared, that's minus 2z squared. minus 2 times minus 2z, that's a plus 4z, and minus 2 times 4, that's a minus 8, right? Minus 8 like this. And now if we simplify the common terms, we're saying we've got z squared, then minus 2z squared minus 2z squared, that's minus 4z squared, minus 4, that's plus 4, that's 8, and minus 8. So this is how we write the equation in the form az cubed plus bz squared plus cz plus d is equal to 0. Okay, so this was looking at the first part, which is number 1. Now let's move on to look at number 2. Okay, so I shall erase this part as well. Okay, so for number 2, what do we know? Number 2, we are told that solve the following equations, giving you solutions in the form x plus yi, iy, where x and y are real. So for the first part, we've got z plus 2i squared is equal to 9. So if we take the square aside, which means you're square rooting both sides, we've got z plus 2i is equal to plus or minus 3. Then z is equal to plus or minus 3 minus 2i. Is that right? Yep. This is what we get. So these are the solutions for z. So saying z is equal to 3 minus 2i or minus 3 minus 2i. Right? Simple as that. Then now looking at part B. Part B, we've got z squared is equal to z plus I squared. So if we expand first, we've got z squared being equal to z squared plus 2zi minus 1. Right? And then if we take z the side, z squared the side, it will cancel, you get a 0. So the 0 is equal to 2zi minus 1. So if we take 1 there, 1 is equal to 2zi, then dividing both sides by 2i, right, z would be equal to 1 over 2i. So this is the solution for z that we get for part B. Then now moving on to number 3. Number 3 requires us to solve the simultaneous equations. Simultaneous equation 3z plus w is equal to 11, then that one as well. So here if we just say let z be equal to x plus iy, right? Then w, here we make w subject of the formula, it will be 11 minus 3z, right? Such that if we were to substitute it in the second equation, we're saying 2iz plus 5 times 11 minus 3z, like that, should give us 8 plus 9i. So 2iz plus 55 minus 15z is equal to 8 plus 9i. And if we take 55 aside, we remain with 2iz minus 15z to give us 9i, and then 8 minus 55, that's minus 47, right? And then if we were to substitute for z by x plus, or one could even do, we could even factor out z, yeah? Right, so factoring out z, we've got 2i minus 15, so like this. Then dividing both sides by 2i minus 15, z is equal to 9i minus 47 over 2i minus 15. Then this division of complex numbers, which we say we multiply both the numerator and the denominator by the complex conjugate of the denominator, right? So z would be equal to 9i times 2i, that would give us 18i squared, which is minus 18. Then 9i times 5, that's plus 45i. Then minus 47 times 2i, that's minus 84, sorry, that's minus 94i. Then minus 47 times 5, we get minus 235, like that. Yes, correct, minus 235. Then over 2i times 2i, that's 4i squared, which is minus 4. Then minus 15 times 5, we get minus 75. Alright, so z is equal to 45 minus 90, 45 minus 94, we get 40 minus 44, sorry, we get minus 49, I, and then minus 18 minus 235, we get a minus 253. Like this is 253, and this over minus 79. Alright, so this is the solution for z, z being x plus I. So x is equal to, so in other words, it's saying z is equal to minus 49 over minus 79i minus 253 over minus 79. Like this, which simplifies to 253 over 79 plus 49 over 79i. This is z. So now calculating the solution for w, we substitute this, and then we simply get our w. Okay, so this is how we solve the simultaneous for number 3. Then now moving on to number 4. Right, number 4 says the complex number 5 plus 2i is a root of equation 2z cubed minus 15z squared plus 8z plus 145 to give us a 0. Now question says find the other roots. So one of the other roots that we know is definite is 5 minus 2i, which is the complex conjugate of this complex number. So to find the second, the last root, what we might do, or what we can do actually, is that we can express these roots as vectors. Then say x minus 5 minus 2i times x minus 5 plus 2i. And then here we get an x squared minus 5x plus 2xi minus 5x plus 25 minus 10i and minus 2xi plus 10i again, and then plus 4, right? So now if we simplify, what can be simplified? 2xi and minus 2xi we cancel, and then minus 10i and 10i we cancel. So we remain with x squared minus 5x minus 5x, we get a minus 10x, and then 25 plus 4, we get a 29. 4 plus 29 like this. So this, right, is a factor. So to find the last factor, we can use long division here, and simply say x squared minus 10x plus 29. We are dividing this into, oh, okay, and my bird, because here in terms of, for x, we're supposed to put z. So let me just make the substitution here. So this z squared minus 10z, right, dividing into 2z cubed minus 15z squared plus 8z plus 145. Like this. So z squared into 2z cubed, this gives us a 2z. Then we multiply 2z cubed minus 20z squared, and then plus 58. So yeah, 58z, like this. And this gives us a 0. Minus 15 plus 20, that's a 5. Z squared, and then 8 minus 58, that's minus 50z. Right? Z into z squared into z squared, that's a plus 5. And now 5 into that, 5 times z squared, that's 5z squared minus 50z. So here would have dropped plus 145. And then 5 times 29, that's 145, such that if we subtract, we get zeros here. So the other root would be 2z plus 5. Sorry, 2z plus 5, this is a factor. So to get a root, we shall solve for z, which will be minus 5 over 2. So the other two roots that we want, we've got 5 minus 2i and minus 5 over 2. So these are the two roots that are required for number 4. Okay, so this was simply solving equations, polynomial equations that involve solutions of complex numbers. So please feel free to leave a comment, drop a like, and don't forget to subscribe. Thank you.